Now let's solve an example problem. The C83-400 red brass rod AB and 2014 T6 aluminum rod BC are joined at the collar B and fixed connected at their ends. If there's no load in the members when temperature 1 is 50 degrees Fahrenheit, determine the average normal stress in each member when temperature 2 is 120 degrees Fahrenheit. Also, how far will the collar be displaced? The cross-sectional area of each member is 1.75 square inches. We're also given a picture of the joined rods with their respective lengths. But before we begin solving for anything, let's use the given find solution format to determine what information we're given and what we need to solve for. We're given the length of brass rod AB on the left, which is 3 feet, and the length of aluminum rod BC, which is 2 feet. I've converted both values into inches for consistency in units. We're also given the cross-sectional area of the rods, which is equal in both, the type of material of each rod, the type of connection at the rod's ends, and the two temperatures we'll be working with. We need to solve for the average normal stress in the brass rod and the aluminum rod, as well as the total displacement of collar B. In the free body diagram in the bottom left, we can see that the walls at point A and C exert forces on the rods to maintain equilibrium in the x direction. The wall at point A exerts a rightward force on the brass rod, and the wall at point C exerts a leftward force on the aluminum rod. Using the equilibrium equation, we see that the force on the brass rod is equal to the force on the aluminum rod, so we can simplify the force term to just F, which represents the internal axial force within the rods. Now we can move on to solving for the total displacement of the collar, which we'll do using the force method of analysis. But first we need to record the coefficient of thermal expansion and the modulus of elasticity of each material. I've written those values here for C83-400 red brass and 2014 T6 aluminum. We'll need these to plug into our compatibility equation. In this case, a suitable compatibility condition would require the displacement of one end of the system with respect to the other end to be equal to 0, since the end supports are fixed connected to the walls. So the displacement of A relative to C is 0. There are two different factors here that are causing displacement. There's thermal expansion being caused by the heat added to the system to increase the temperature from 50 degrees to 120 degrees. And then there's contraction being caused by the two loads of magnitude F caused by the walls that are pushing on the rods and holding them in place. However, since the rods are fixed in place, the entire system is in equilibrium, and so the expansion caused by heat must be balanced out by the contraction caused by compression. Be sure to review the previous key concept video on axial loads to review the formulas for thermal displacement and load displacement relationships. I've written them here, but notice that each rod's displacement must be calculated separately since they're made of different materials and are of different lengths. To solve for the thermal expansion terms, we plug in the respective thermal expansion coefficients, the changes in temperature, and the initial lengths of the brass and aluminum rods. To solve for the contraction caused by the compressive forces, we plug in the initial lengths, the cross-sectional areas, and the modulus of elasticity of both rods. The only thing we don't know is the internal axial force F, so we leave the contraction displacement in terms of F for just a second. To solve for F, remember that the total expansion must equal the total contraction, since the rods are fixed against the walls and therefore are unable to actually expand or contract. So the sum of the displacements must be 0. Expansion is considered positive displacement, and contraction is considered negative displacement in this case. So when we plug in the values we just calculated, we can simplify and solve for the internal axial force F, which ends up being 17,093.4 pounds. Great. Now we can solve for the average normal stress in each member. They should be equal to each other since the entire system experiences the same internal axial force and has the same cross-sectional area. Remember that average normal stress is force over area, which in this case is 9.77 kilopounds per square inch. We just want to check that this design is mechanically sound and under the allowable yield stress. So we confirm that our calculated stresses are less than the yield stresses for C83-400 red brass and 2014 T6 aluminum, which they are. And lastly, we can calculate the displacement at collar B. Remember that our compatibility equation requires that the displacement of rod AB is equal in magnitude and opposite in direction of the displacement of rod BC. The same must also apply to the displacement of collar B, since that is also a part of the system. Therefore, the displacement of all three sections must be equal. Let's pick the displacement of the brass rod to calculate, since we have all the numbers for that already. Subbing the values we calculated before thermal expansion and compressive force contraction, and the value for the internal axial force F, we get a total displacement of 6.114 times 10 to the negative fourth inches. Perfect. I hope this two-part lecture and example series helped bridge the gap in your understanding of axial loads. If you have any questions about this topic, feel free to ask in the comments below. Thanks for watching.